Hi, I'm Swashni Ramanathan, and this is my Teach One presentation for class HAP 823 on the topic Causal Networks. In this question, we are asked to draw networks based on the following independence assumptions, and we are also asked to predict the last variable in the network from marginal and pairwise conditional probabilities. I'm giving a little introduction before jumping into the answers. What is DAG? I'm giving the definition right now. A DAG represents the causal relations in a given population with a set of vertices V when there is an edge from A to B if and only if A is a direct cause of B relative to V. I have three diagrams to explain it well. I'm going to start from below. X and Y are independent. Y gives X, which is number B, and X gives Y. The next topic to understand to answer this question is variable elimination. You can see a DAG diagram given here as an example. Probability of A and probability of B given A and C and probability of C. Please take a minute to understand these three steps that are given here. The initial factors are probability of A, C, B given A and C. For an order of A, C, in the first order F1, we are eliminating A and this is how we write the equation. And in the next order, we are eliminating C and this is how you write the equation. Then we renormalize to get probability of B. Again, I'm repeating it. Please take a minute to understand this very well and then we can proceed to answers. This is our first question where the nodes x, y, z are given and the assumption is x and y are independent of each other. There are two screenshots here. The first picture, you can see all the combinations of x, y and z and the correct answer is E, which is having a common effect where x and y are independent of each other but they just have a common effect z. That's the right answer. And in this picture on the right, you can see two paths, active and inactive, and you can see that x and y are inactive and they just have a common effect which is z. This is the second question, which is similar to the first one, but we have an extra part where not independent x, y given z. So for this question, we follow the variable elimination method after doing this active and inactive part. Then we order it by x, y. First we eliminate x, then we find the probability of y, z, and that's the first equation is the first step. Then we eliminate y, then that's the equation, and then we just normalize z. In this question, three nodes x, y, z, and the assumption is independent x and y and independent y and x and y given z. So the only possibility is all the three are inactive and you can see the answer circle first, that x given y and z and y given x, all the three are independent of each other. The next step is y measured last. So we measure y. Since everything is independent of each other, the probability of y is just the sum of all the three variables. This fourth question could be a little tricky. There are four nodes x, y, z and w, and there are three assumptions made, and w is the last one for which we'll be finding the probability of w towards the end. So for each assumption, there is a diagram below, so you can see three circle diagrams below. The first assumption is pretty straightforward where x and y are independent. So there are no direct contacts between x and y. So y gives w and x gives z. So the condition is satisfied. For the second question, independent x comma y given z. So uh, in the same way, the active part is z, where y gives w and x gives z. And for the next part, x comma y and w gives z. So the active part becomes y, where y gives w and that gives z because w given z, and then x gives z. So in the end, each and every path directly gives z in a way. So that's the explanation for the assumption. And then for the probability of W, we use variance elimination, where we eliminate x, y, and z. In the first order, we eliminate x, and that's the formula. And then we eliminate y, where in F2, W is equal to probability of y given W given y, and then we eliminate z. For the probability of W, we normalize F2 and F3. The fifth question is pretty simple. There are four nodes x, y, z, and w, and there are two assumptions independent x, y and independent z, w. The only DAG diagram that could satisfy this assumption is z is independent of all the variables and w is having a common effect from x and y. So that's the only criteria that can satisfy this assumption. And we are asked to measure W. So we use the same variable elimination method and we eliminate in the order of x comma y, and that's the um, that's the formula where which we'll use to find the probability of W. Thank you.